Alright, in this video we're going to talk about acids and bases. Make sure you listen carefully as we go along so you know the differences. And we're just going to talk about some general differences, then we're going to get real specific here in a minute. Acids and bases. Alright, so let's start at the top. The very first thing, acids are sour and bases are bitter. Now you may think, oh, okay, well I'm in a chemistry class. I'm never going to put an acid in my mouth. That's right, you're not going to put an acid from a chemistry lab into your mouth, but we eat a lot of different acids in the world. If you've ever eaten these really sour candies, Cabbage Patch Kids, or some of these other kinds of candies, these really sour, they put citric acid in it, which is found in lemons, and they put in an extreme amount so that it's sour tasting. And so there are lots of acids in the world. There's hundreds of them. Some of them we eat and drink. The really strong ones in lab we do not. Bases are bitter. An example of, and some students struggle with the difference between sour and bitter. Bitter is more like dark chocolate. Now you may like milk chocolate like a Hershey bar, but I'm talking about really, really dark chocolate. It has a really bitter taste. The darker that it is, that it's less sugar. So chocolate itself has a very bitter taste. So acids are sour, bases are bitter. The second thing, acids have an H plus in the front. And actually I'm going to write that a little different. They're going to have an H in the front. Bases, on the other hand, are going to have OH at the end. Now let me explain in detail what that means for you real quick. Here's an example of an acid, HCl. When you drop it into water, it's going to break into this plus this floating around. Alright, this is what makes an acid so strong. I'm going to use a silly example here, but let's think of it sort of as a Pac-Man. He's going to eat away at things, and so really strong acids can eat away. So like if you eat too many lemons or too many of those sour candies, you get sores in your mouth. But a really strong acid like hydrochloric acid, which is used in your pool, or its stomach acid, really strong acid is like a Pac-Man. Waka, 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 waka. It's going to eat away at something. Okay. Bases, on the other hand, an example of that is NaOH. This is the active ingredient in Drano. Drano you pour in your pipes and it eats through hair, grease, and grime in your pipe. It breaks into these things. This is what makes a base so strong. So using sort of the same scenario here, this one is Miss Pac-Man. Now the reason I said, now that's a horrible drawing, I know, but just to get it across to us, these both eat away at things. They just do it in a different way. Acids, the more H you have floating around in a solution, the stronger it is. The more OH in a base, the stronger it is. And I'm going to give you some hints on some other things, but you'll notice that when I drop this in water, I get H++ Cl. That word was dissociation, and we already learned that word. It dissociates in water. So every one of these molecules breaks, and you have lots and lots of these floating around. And this doesn't really matter. It's what they sometimes call a spectator ion. It's just sort of watching. It's just sitting there. It's not doing anything. This is what makes the acid so strong. Same thing is true for a base. When you drop something like sodium hydroxide in water, the sodium ions are sort of the spectator ion. They're just sort of sitting there. But it's these OHs that eat away at something. Okay? And so that's one of the biggest differences. Okay? So H in the front, when you look at the formula, that's going to be a dead giveaway that it's an acid. OH at the end, it's going to be a dead giveaway at bases. Now we're going to have to deal with those definitions here in a minute. But those are the easiest ways to remember them for right now. We'll do more details here in a minute. Now, what I want to do that matches both of them, and we'll put that one back in there real quick. H in the front. And they were sour. What I want to talk about next is what is called a neutralization reaction, and that's my abbreviation for reaction, neutralization reaction. Whenever an H plus runs into an OH minus, it is called a neutralization reaction, and basically they knock each other out. Now, using the scenario I already had, Pac-Man and Miss Pac-Man knock each other out. They're both very strong, but they're both very strong in different ways. They knock each other out. Let me give you an example of what happens, a real example. Let's go ahead and take those two we just had, hydrochloric acid and sodium hydroxide. Now, we learned earlier in the year that this is what is called a double replacement reaction, plus minus, plus minus. You might have learned it as boy, girl, they're dancing. That boy's dancing with that girl, that boy's dancing with that girl. So when you switch sides, Na, that boy is going to dance with that girl, Cl, or plus minus, however you learned it. And H is going to be with OH. Now, HOH, for example, is what is known as water. Okay, it's another way of writing it, HOH. We'll just leave it like that for a second. Now, my quick question for you is this. Is that an acid? Does it start with an H? No. Does it end in an OH? So is it a base? No. But look at this one right here. It has H in the front, which means it's like an acid. And it has an OH at the end, which is like a base. And I already told you it's water. But water does not taste sour. It's not bitter. And it doesn't have acid or base properties. They knock each other out. HOH knock each other out. And they end up being neutral on the pH scale. Now, we'll talk about the pH scale in a minute. And I use that word because you've probably heard it before. Now, what is really happening is this. Whenever you have a strong acid, make sure you write this down, with a strong base, and you may be thinking, I don't know which is which. Don't worry, I'll teach you in a second. Strong acid plus a strong base always makes something called a salt plus water every time. A salt plus water. Now, there are lots of kinds of salts in the world. This one happens to be the salt that you and I eat when we salt our foods. Let me take a completely different example, and let me show you how this one works. I'm going to take another strong acid, sulfuric acid, H2SO4, and I'm going to put it with lithium hydroxide, which is a strong base. In just a second, I'm going to tell you how you know the difference between a strong acid and a strong base. When you put them together, plus, minus, Li is going to be with SO4. Now, I already switched the charges for you. And H is with OH. Now, I'm not going to balance everything out, but you'll notice here's what happens. Strong acid, strong base. Look, it made water again. And it made a kind of salt. Now, ladies, you will know there's different kinds of salts in the world because there are bath salts, and there's all kinds of examples of salts in the world. Bath salts that you put in the water to make, when you take a bath, smell good, or the water feels a little bit different. These generic things are called salts. It's not an acid. It's not a base. You can tell by looking at the formula. So whenever you have a strong acid and a strong base, they knock each other out, and they end up being neutral. Okay? So you have a neutralization reaction. So acids and bases are both very, very strong for different reasons. These have H's, these have OH's. And when those H's and OH's run into each other, they knock each other out. Now, next thing I want to talk about are what are the strong acids and the strong bases. Okay? So let's talk about strong acid, strong base. First thing, they both have to have 100% dissociation. Means when you drop them into water, they all break up. All the molecules break up. Now, let me give you an example real quick. I said a while ago, there's hundreds of acids in the world. You drink some of them when you drink a soda. Carbonic acid and phosphoric acid are both found in sodas. Do you think they're a strong acid? No way. You wouldn't drink them. Okay, so what happens is they don't break down, they don't dissociate to let all those H's go to cause damage. Now, if you drink too many Cokes, yes, it can upset your stomach because you drank too much of the liquid, but in that liquid itself, not every molecule breaks. Remember, the more H's you have, the stronger it is. The more OH's you have, the stronger it is for a base. Okay? So let's do it this way. There's 5 strong acids. You'll want to remember these. HCl, H2SO4, HNO3, HBr, and HI. You may want to pause the video to catch up to me. Now I'm going to go ahead and write the names. Hydrochloric, sulfuric, nitric, hydrobromic, and hydroiodic. These are the 5 that we feel like the state is going to use as the 5 strongest. Now, are they all used in the same way? No. Hydrochloric acid is what's made in your stomach to break down your food. Sulfuric is battery acid. Nitric acid is used in industry a lot, would not have a common use that you would use. Hydrobromic and hydroiodic do not have everyday uses either. But what they do is they 100% dissociate. So when you dump them in water, every one of these molecules that you see right here, all the H's break off of them. So you have all these little Pac-Mans running around ready to eat away at something. Okay? The strong bases, again, have 100% dissociation. But here's the easy way to remember them. Column number 1 plus OH. Column number 1 plus OH. Let me see if I can make that make sense. If you look at your periodic table, anybody in the first column with OH is a strong base. Lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide. Now, francium is radioactive, so we don't have a lot of it in the world, so having francium hydroxide would be incredibly rare, but lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, all the strong bases. So that makes it real easy to remember. Now, let me give you another hint since I'm using the chart. Hydrochloric, HCl, hydrobromic, hydroiodic. Hydrochloric, hydrobromic, hydroiodic. So if you're looking, we're looking at these columns. There's a fast way to use your chart to help you. Strongest things with OH are bases. These with an H on the front. Hydrochloric, hydrobromic, hydroiodic. The other 3 you're going to have to sort of memorize here in the middle. Sulfuric and nitric, or the other 2, excuse me. Sulfuric and nitric. These are the strong acids and the strong bases. They have 100% dissociation. So, now that you have those, let me ask you a couple of examples. What if you're given something like this? H2CO3, carbonic acid, strong or weak acid? Well, you have to look at your list. When you learn your list, is that one of the 5? No. Carbonic acid is considered a weak acid. Why? Because it's not one of the 5. It's that simple. Anything that's not one of those 5 or any of column number 1 plus OH are not strong acids or strong bases. They're weak. And so carbonic acid being one of those I said a while ago that we find in sodas. Okay? So you have strong acids, strong bases. Now it goes back to what strong and weak electrolytes are. They break down or have 100% dissociation. So you can see how all these topics sort of go together. All right? So you have strong acids and strong bases. In the next video, we're going to talk about how do we know what these strengths will do for us.